In this video, we are going to discuss about or rather to visualize a series as a function, right? So to begin with that, let's revisit the geometric series that we did before. So remember, if we have this format a times Rn, which is the geometric series, we were able to show that the sum of a geometric series is equal to A divided by 1 minus R for the common ratio with the modulus less than 1. Now let's replace A with 1, right? Replace A with 1 and let's rewrite R with the simple variable x, right? Okay, so then what we have will be x to the power n starting from n equals 0, and that means this series or the combination of the addition of these terms will be equal to 1 divided by 1 minus x, where the modulus of x is less than 1, right? Now we can even relate this series to the power series knowledge that we learned before. See here, this is of the format Cn to the power x minus a to the power n, where Cn is the sequence of 1, the constant sequence 1, and a is 0 in this case, right? So this is a power series, like this is in the power series notation, right? So just forget about these stuffs for a moment, and then since we have a power series, now we can compute the radius of convergence, right? So for that, to compute that, we can see an is equal to here an is equal to x to the power n, therefore an plus 1 is this one. Then when you get the ratio of these two things, you will end up with the modulus of x. So from the ratio test, we can say that this series will converge when the limit, that means this one, so that is when the modulus of x is less than 1, the series will converge. These are the theory that we learned for the power series, and it will diverge when the limit is greater than 1. And also to check the endpoints, we will separately substitute the two endpoints to the series and check for the convergence. And you can see for both these endpoints, the series diverges, and you can say it directly from the divergence test. The limit of an was not equal to 0 in both these cases, right? Therefore, the interval of convergence of this series from the power series knowledge, we can say that the interval of convergence is -1 to 1 with open brackets, right? In other words, this x, you don't have any equal marks here, so both this notation and this notation means the same, right? So now see, here we did not use anything about any knowledge about geometric series. We totally did this with the knowledge we have in power series. But here without discussing anything about a power series, we were able to, with those fundamental ideas about the convergence of a series, we computed this result, right? And in both these cases, we had the same feasible region for the x values, right? So even from the theory of power series as well as from the theory of geometric series, we had the same region, right? And so now by any method, what we have finally concluded is that for these set of x values, the series will converge. In other words, for these set of x values, the series will give a finite value, right? That's the most important part in here. Now, let's move to this equation which illustrates the behavior of the series, right? So we have already computed this one, and now we can see that let's have it like this. Now if we name a function, or if we define a function as 1 divided by 1 minus x, you can see that this is a function on the set of real numbers except 1, right? So the domain of this function is all the set of real numbers except 1 because of this 1 minus x nature, right? And you can see that we have equated the series with the function, right? So we have equated the series with the function like this. Now, if the function and the series are equal, then when you input a certain x value, both right hand side as well as the left hand side should give the same value, right? Say for example, if we input x equals 10, let's see what will happen. So the function value at 10 will be equal to 1 divided by 9, negative 1 divided by 9, right? And when you substitute x equals 10 in the series, what you will get is this one, right? So this of course will be a very large number, right? It's like we are adding the powers of 10, which will definitely go to infinity, right? But see, these two are not equal, although we have written down a equation with these two terms. So where did we make the mistake? That mistake comes with this feasible region for the series. Now this explains the reason behind this error, right? So here what we should identify is that the series will behave as a function only within the region of convergence, right? So within the region of convergence, now this is very important, okay? So within the interval of convergence for these x values, when x is in this interval, that is, now this is the symbol for an element, right? So when x is an element of this set, then both fx and the series are equal. So if we are taking an element from this set, let's say for example x is equal to negative 0.5, then both the function value negative 0.5, that is 1 minus negative 0.5, and that is equal to 1 over 1.5. So this is the function value and the value that you get from the series should be the same. So when you add up all these terms, you should get 1 over 1.5. So what I want to highlight here is within the interval of convergence, when x is in the interval of convergence, the power series will behave as a function, but outside that region it will not. Now remember, now you have to notice this one, okay? Now this function will behave outside this region, right? So if you take an x outside this region, then that will make no harm to the function. So function will take its own path outside this region, but series does not. Series cannot handle the x values outside its interval of convergence. So now you have to keep in mind that the power series will behave as a function within the interval of convergence. And there's another important thing that you should memorize, that is this equation, right? This is a very important basic equation that you have to have in mind, okay? Because from this, now here what we have done is we have written down a series as a function, as a representation of a function, right? So this representation is very important because from this one you can generate several other function representations for different types of series, and I will do it in the next video sets. So for the time being, what you should understand is that first of all, the power series will behave as a function within the radius of convergence. And for our special power series, this one will be equal to 1 over 1 minus x when x is less than 1. So now remember, what do we mean by a domain of a function? That is the feasible values for the given function. Now for this function, if you consider this as a function, the domain of that function will be all the real numbers except 1. But if you consider this series, the domain of this series will be this value. So if you say the domain of the series, that means we are referring to the interval of convergence. So we learned a new term here, the domain of the series, right? That is basically the same as the interval of convergence, right? Okay, so and this is an important equation that you should keep in mind, and along with this feasible region, okay, all these things comes together. And in the next couple of videos we will see some alterations to this values in this equation, and then we can obtain different types of function, like we can extract out different functions from this basic equation.